Good morning, everybody. This is James here with you all for class number 2 of the Market Farming Immersion course. I wanted to say thank you for your flexibility and resilience in the face of these current developments. I think these events, although unfortunate, are in reality going to shift some attention to the need to expand local food systems, and I'm glad that you all have invested yourselves in this class. Today, we're going to be talking about soil in the context of regenerative ag. Organic and regenerative agricultures manage crop health and yield by improving soil health, whereas industrial and conventional agricultures destroy soil health and therefore must manage crop health and yield with chemicals. We'll try to demystify soil today by looking at its different components and how you as a grower can accelerate, not impede, your soil's natural trajectory towards health and function. Hopefully you're all cozied up with something to drink and something to take notes with. Please write down things that stick out for you or things that you maybe need clarification on. You will have a writing assignment after the prezo, so taking some notes will help. Let's go ahead and get started. So before we get into the how of building healthy soil, let's ask why we want to build healthy soil in the first place, because that's going to take resources from us. So what's the concept? Why is it important? What are the benefits? So if we distill the concept down as much as possible, it'd probably read something like this: healthy soil equals healthy plants. I think most folks would agree that an organism's environment is a major determinant of the health of that organism. So if we transpose that over, we would say that the health of the plant is determined by the environment in which it's grown, which is the soil. You see, in conventional agriculture, soil health is typically very degraded, and when the plants have problems as a result, chemicals are used to prop the plants up. It's kind of like keeping the plants on life support. But as organic and regenerative producers, we don't have those same chemicals in our toolbox, nor do we really want them. So we have a different strategy. We're going to focus on improving the soil environment, the soil health, in hopes that that in turn grows healthy plants. Healthy soil is definitely a more functional soil. It's going to maintain that ideal balance that we're looking for of water, nutrients, and air that most plants prefer. It's when we disrupt this balance that we see adverse reactions in plants. Healthy soil environment is balanced in that way, but it's also balanced in a biological way. A healthy soil environment will support a diverse array of beneficial soil organisms. We read about these organisms, right? Read about the worms, the protozoa, the bacteria, the fungi, the nematodes. That array of soil organisms, that is the soil food web, and a diverse soil food web creates an environment where soil-borne diseases and soil-borne pests aren't able to get a strong foothold. Kind of like checks and balances. Okay, because healthy soils cycle water and minerals so efficiently, inputs like irrigation and fertilizer are decreased. Healthy plants also are going to have a greater immunity to pest and disease, which means less pest management inputs on your end as the farmer. Okay, this is in parentheses because maybe this doesn't really affect your bottom line directly, but this is, still a very important part of the conversation, and that is healthy soil performs many vital ecological services in the environment. So by focusing on building healthy soil, we are contributing to a healthier environment. Some of these services, I'll just name off a few, some big ones: filtering groundwater. Soil can sequester vast amounts of carbon from the air. It can also reduce eutrophication in our waterways. So those are just a few. Also, while we're reducing the need for external inputs, right, input reduction, um, that also is going to help us reduce our environmental footprint, right? Because we're having to buy less, we're having to consume less inputs. So today we're kind of talking about three different buckets when we're looking at soil. The first one's soil structure, the next one is soil biology, and the third one's soil chemistry. So when we're talking about soil structure, we're talking about the physical composition of the soil. So that includes what you read about, the composition of sand particles, clay particles, silt particles. But wherever you're at, whether you have a sandy soil, a clay soil, or a loam soil, you still can work towards having good soil structure. And what builds good soil structure is the soil food web. You read about the soil food web. We're going to talk more about the soil food web, but this is the soil food chain, if you will. It's more accurately described as a web, but it's the complex matrix of all these different soil organisms and their interactions. Those interactions of those soil organisms helps build the soil structure, right? We read about soil aggregation and how the soil particles are glued together by those microbial glues, right? The glomalin, to allow pore space in between the soil particles, which allows for that proper balance of air and water. So on the left here, we have a good soil structure. So the top part there, where it has the arrow pointing to the topsoil, you can see the aggregation. You can see the soil particles, but you can also see the pore space between them. And those soil particles are being held together by those microbial glues, a byproduct of the soil food web. Okay, and then underneath we have what we would expect. We have the subsoil, right, which is not the topsoil. It's the next horizon down. It's the layer that has less biological activity. It's going to have less pore space, less nutrients as a result. On the right, we have compacted soil. Okay, when we look at that tight structure in the topsoil, we don't see that same pore space anymore. We see that it's pretty much devoid of pore space. We also see crusting on the top. We also see between the very bottom layer and the layer below the topsoil, we see a hard pan compaction layer. Okay, this is the result of tillage. Tillage, and we read about this, but just to reiterate, when you till, you're affecting the soil in multiple ways. The first thing you're doing is you're taking that beautiful aggregation that we see on the left, you're taking that and you're basically throwing it into a blender, okay? You're blending all of that that soil material essentially into like a fine dust or powder, thus collapsing all of that pore space. That's why you see that tight structure in the diagram on the right. Also, when you blend up the soil like that, as it settles, the heavier particles, the sand particles, are going to migrate towards the bottom, and the lighter particles, the finer particles, the clay particles, are going to rise to the top. Well, once those clay particles are on the surface and they get wet, they're essentially going to harden like pottery would. And that's how you get that soil crusting on the top, which is going to reduce water infiltration, right? It's also going to reduce air exchange. The other thing that is happening when you till is the sheer force of those tines. The bottom boundary of what they reach in the soil, as they're hitting that bottom boundary, they're smacking it very hard. There's a lot of mechanical force behind a tiller, so it's churning up the soil, but at the bottom boundary of its reach, it's actually smacking the soil. And it does that in a way that compacts that profile and creates what's called hard pan. Hard pan is going to reduce water infiltration, and it's also going to reduce air exchange as well. So we're going to tune into this video.
What you do is you collect your soil, one from the area you do a lot of tillage and the area you don't do a lot of tillage. This particular soil came from Ray Steyer's farm, and he has been doing no-till for 40 years. The only piece of equipment he runs there is a sprayer or a no-till drill. This one, it comes from the neighbors. Same soil type, by the way, and he grows vegetables continuously, year after year after year. That's the major difference between the soils. As you can notice, the color, it's quite different. This one's darker, this one's lighter. So the way this test works is, what I'm going to do is I'm going to place both these aggregates inside the water. In each aggregate, there's billions and billions of pore spaces. As I place them into the water is going to rush in to fill those pore spaces. And what we want to see is, will this aggregate hold against those forces and not fall apart? Okay. The contrast here is, notice that the jar is clear here. This one is not clear. Notice how the aggregate completely fell apart. What this means is the soil pores are collapsed on this particular aggregate. These ones are still intact. What's so important about that is the more pore spaces you have in the soil system, the better the infiltration. The colors differentiation between the two glass cylinders. One is clear and one still clouded with suspended clay particles. This one is still clear, and notice the aggregate's still intact for the most part. Some of it fell to the bottom, but still a majority of it's still intact. And the reason for that is that a lot of these biological cementing glues are hydrophobic. They can repel water, but yet they still hold the particles together. This one here had very, very little, no cementing agents, no biological glues holding it, so all of it fell apart and landed up in the bottom of the glass cylinder. I use this test, it's called the miniature rain simulator, to build upon the point of the slake test. The slake test and the rain simulator test are very related. When you have no pore space, you have no infiltration. So this whole demo is to show what happens when you have pore infiltration. So I collected the soil from a conventional till system, agro system, and a no-till agro system. The difference between these two systems, this one has not been tilled in 40 years. This one's continuously tilled every year to grow vegetables. Same soil types, but what we want to do is we want to show which one infiltrates first, which one goes through that profile. Notice that the soils are, the jars are plastic jars, yarn jars, are filled up a quarter of the way up on both jars. What we're going to do is we're going to pour this colored water. One is blue and one is blue red. That's the only, it's just plain colored water. And the only reason I do that is to show the water column building up as we pour in. And what we have here is that we have two little plastic containers that we're going to simulate the rain. Notice in the no-till system how the water infiltrated through the whole profile. Notice on this side, the water is still standing up in a column. This shows that in most of our watersheds, we have an infiltration problem, not a runoff problem. And what I mean by that is If we focus on the infiltration problem, on soil health, soil function, then we will focus on what we have to do to make that soil healthy. Notice on this one, the water will go through the soil, and from the soil it'll go right into the lakes, into the rivers, into the lakes. This one here, the water will shut off the land, take all the fertilizer and all the pesticides with it. So this one, notice how it has not infiltrated through. Look at this one. And this, now what causes this is when you do tillage, the zygomycosis bacteria will start breaking down all the glues that hold the particles together, the soil structure together, and the pore spaces collapse. You remember on the slake test, how the soil fell apart? Well, there's no glues to hold the particles together. And this is exactly what happens. There's no pore space. This one has pore space, lots and lots of pore space. The soil is held intact by the glues created by all the organisms, soil organisms. This one does not. The water right here ran off into our rivers and into our lakes. This is to show us what happens when our soils do not function properly. Our soils have this incredible way of working. They not only infiltrate water, but they also capture water because of the organic matter. Soils have this incredible ability to filtrate and to capture. Healthy soil systems not only capture and hold water better, but they also allow it to pass through. In unhealthy soil systems, that's not the case. Our soils are designed to filtrate and to clean our waters. So that's part of that whole process. The whole picture here really is, the takeaway is that we want water in the soil system. And that's why when it rains 1 inch, we're going to get all that 1 inch. You're not losing anything. That's the beauty about this. It shows that you're capturing all the water so that when droughts do come, that you can capture every precious inch of water. That's the whole thing.
Okay, so a practical field test we can do for determining, how much clay or sand a soil has is the roll test. So we can grab some soil and we can roll it into a clod, like a little turd. And if it holds its shape, it means that it has a good clay component to it, right? If it didn't hold its shape, it would be a very sandy soil, right? If you just took sand and tried to wad it into a ball, it wouldn't hold its shape, it'd fall apart. So this holds its shape on its own, so it's got a clay component. If you flick it, does it crumble? If it crumbles, it's also got a sand component to it, right? If it didn't crumble at all, that would be considered a heavy clay. So if it holds its shape, but it also crumbles when you flick it, that's usually when you're in the loam zone. Yeah. All right, so this is a little experiment, really easy to set up. It's how we can further bring home that point of no-till. So we have 2 plates here, one with white flour and one with bread, okay? And we're gonna look at the one with flour first. The flour represents tilled soil, right? That soil has been grinded to dust and it's settled. We've lost that pore space, we've lost that aggregation. We're gonna do a little rain simulation here. We're gonna simulate what happens when rain falls on this type of soil. Can you get it close up a little bit? Kind of like an overhead. So look at what's happening. We have poor infiltration. The water is actually not able to percolate through the soil because all that pore space is collapsed. So it really just sits on top. A lot of it is run off to the sides. So that's representative of that water picking up whatever's on the field, fertilizers, pesticides, soil, and it's running to the streams and rivers. And you can see the turbidity of the water carrying that material. But if we dig around in here, right underneath the surface, where we're starting to get that crusting, it's dry. It's as dry as it was before it rained. The water is not infiltrating through the soil strata. Okay, so that's tilled agriculture, right? No pore space. We're gonna do the same experiment over here with the bread. Do our little rainfall simulator. Now, as the water's hitting the bread, let me zoom out here for a second. It's infiltrating, right? Because what does the bread have that the flour doesn't? It has that pore space, so the water is able to infiltrate through. And as it's infiltrating through, it's drawing fresh air in, and that water is making its way down to the groundwater. Very little water ran off, right? The bread is very absorbent, and that's what good soil does. It absorbs and infiltrates water. And if you look at the difference, what's the difference between, with this analogy, what's the difference between the flour and the bread? They both come from the same material, they both come from flour, but the difference with the bread is it's gone through a biological process with the yeast, which has created that pore space in the bread. And if we look under here, we're wet all the way through the first piece, and we're moist on the second piece. So the water was able to infiltrate through down into the soil strata where it can be captured and stored. That's a wrap. So how do we work to repair or improve our soil structure where it is now? So the first thing you want to do is you want to stop tillage, because tillage by nature degrades the soil structure. As we just saw, it grinds everything up into a dust. It collapses all of that pore space. It destroys those microbial glues that hold the aggregates together, and as a result reduces the soil's ability to function, reduces the soil's ability to infiltrate water and air. So we have to stop tillage. We also don't want to spray any harmful biocides. Remember that soil structure is a byproduct, it's a result of the soil food web, all of those living organisms and their interactions. If we spray pesticides or fungicides, we are going to negatively impact that soil food web and its ability to build or repair soil structure. We want to shield the soil with mulches. We want to protect it. So we may have stopped tillage, which is a very detrimental mechanical force, but also leaving soil bare and exposed to the elements is also going to make you vulnerable to a decrease in soil structure. So, for example, if you have bare soil and a 2-inch rain event comes through, like a thunderstorm, the actual force of the water impounding on the soil is going to have an effect not as extreme as tillage, not as pronounced, but very similar. It's going to compact the soil. It's going to blend the soil in a way that allows those clay particles again to rise to the top after it settles out of solution, and you're going to get the crusting. You're also going to leave the soil more vulnerable to erosion from the force of that water, and also if you have your garden sited in a particularly windy location, you can experience wind erosion too. So covering the soil with mulch is paramount. And then obviously we want to support the soil food web, and the best way to do that is to feed the soil food web. What does the soil food web eat? It eats organic material. So we're going to go over what some sources of feedstocks are a little bit later in the slideshow. So mulching is a great way to work towards soil health, and it gives you a lot of bang for your buck. So let's look at some of the benefits of mulching. We discussed this in the last slide. It's like a shield. It protects the soil surface from erosion from heavy rainfall events, erosion from wind. By protecting the soil from erosion related to rainfall, it's also going to mitigate that crusting effect we talked about when the rainwater turbulently impacts the soil. It blends it up, and those clay particles settle to the top and give you that crusting effect. So we want to avoid that. Mulch definitely helps. Mulch conserves moisture for sure. So if you do a side-by-side with bare soil and mulch soil, the bare soil is going to have a much higher rate of evaporation than the soil that is mulched. Moderating temperature. So mulch can be seen as a type of insulation, really, on top of the soil surface, and what it's insulating is the geothermal temperature of the earth. So what this means is using mulch in the winter is going to keep your plants a little warmer. Using mulch in the summer is going to keep your plants a little cooler. Mulch is also going to help you reduce weeds. I mean, if you look at this picture, you see a few weeds popping up, but they're really of little consequence because they're so sparse. If this soil was bare, this would look entirely different. The weeds would probably be outgrowing these onions, but by having this thick layer of mulch, we don't invite the weeds. We don't create a niche for weeds to thrive. Weeds thrive in bare exposed soil, not in heavily mulched soils. Another thing you'll notice, when you start digging around in a mulched bed, is you'll start noticing lots of life. You'll see garter snakes, you'll see spiders, you'll see earthworms. This mulch creates like a habitat, like a micro habitat for all of these beneficial soil organisms, which in turn really help keep pests in check. And ultimately, this mulch is organic matter, right? It's organic matter is matter that is living or has once lived. This mulch came from a crop of wheatgrass, so it was once alive. It is organic matter. That means that it can be decomposed and reincorporated back into the soil. So over time, with moisture and the microbial action of the soil food web, this mulch will slowly break down and be added back to the soil. So we've mentioned the soil food web quite a few times. The main idea here is that the soil food web, which again are all of these organisms that operate like their own little ecosystem down in the soil. The idea is that if we feed that soil food web, the soil food web will actually feed the plants. We don't have to feed the plants directly. We feed the soil, and the soil feeds the plants. Here's a video that kind of helps explain.
So in this soil are billions of lives. We have microbes that are in the soil, and the plant builds a relationship with these microbes. So I'd like to tell you kind of how the system falls into place. The soil food web is made up of an incredible diversity of organisms. They range in size from the tiniest one-celled bacteria, algae, fungi, and protozoa to the more complex nematodes and microarthropods, to the visible earthworms, insects, small vertebrates, and plants. As these organisms eat, grow, and move through the soil, they make it possible to have clean air, water, healthy plants, and they moderate water flow. So let's take a close look at what happens in the soil food web. So the plants take in sunlight and secrete carbohydrates and proteins, some of which are then excreted through the roots and into the rhizosphere. So that's the area right around the roots. Bacteria and fungi are attracted to the roots to consume the excrements and sloughed off cells from the roots. The bacteria and fungi are eaten by the protozoa and the nematodes, and the nutrients that the protozoa and nematodes don't need are released as nutrients for the plants in the rhizosphere. Protozoa and nematodes are eaten by arthropods, and arthropods are the insects that have segmented bodies, such as spiders, moths, flies, grasshoppers, butterflies, bees, ants, beetles, and more. So the arthropods are eaten by snakes, toads, birds, and other animals. Earthworms that live in the soil eat bacteria, fungi, protozoas, and nematodes. So if you have a healthy worm population, then you have a healthy soil food web. So all dead plants, animals, and bugs are eaten by the bacteria and the fungi and add nutrients to the soil. Animal dung is consumed by the bacteria and the fungi and also adds nutrients back to the soil. So all of the eating and decomposing has byproducts of nutrients that feed the plants, and the soil food web is a delicate structure. If one player is removed from the game, then the food web can be disrupted and not work. So the soil food web is critical to what's going on in our garden. Now, if you want some heavy-duty reading, try this book, Teaming with Microbes. This is by Jeff Lowenfeld and Wayne Lewis. And this describes everything in nitty-gritty detail, and it has microscope pictures so you can actually see the fungi and the protozoas, and it's an incredible book. A little bit of a heavy read. You'll just have to go through it slowly. But anyhow, if you want more details, here it is. Oh my gosh, it's a great book. Okay, so now that we know that we have this living soil food web down here, what are its purposes? So one of the things that the soil food web does is it'll take the nutrients from decomposing plant materials, compost, even some of the rocks and stuff. It breaks all that down so that the plants, it makes it plant available, so the plants can absorb the nutrients. So the microbes are critical to the plants being able to absorb all the nutrients that they need. When the plants can absorb all the nutrients that they need, then the nutrients are available to us.
So if we understand that we need to team up with the soil food web to achieve soil structure, soil health, soil function, we got to know what to feed them. And there's a few different ways we can do that. Let's check out this video first. This is a really, really cool video from Kiss the Ground.
Do you feel hopeless about climate change and the damage we are doing to our planet? I did. But then I was shown a new way to look at the problem, which made the solution so obvious and so within reach. A solution that's right under our feet. Climate change is all about too much carbon in our atmosphere. But carbon's not our enemy. It's the building block of life. Everything alive is made of it. It's us. The problem and the solution are simply a matter of balance. Let's step back and look at the 5 pools of where carbon is stored on planet Earth. Starting about 500 million years ago, when plants appeared on land, carbon began to cycle in an amazing balance, a balance that allowed for life as we know it to evolve. Then one life form, us, figured out how to extract carbon from the fossil pool. Then we burned it for energy, putting it into play, disrupting that balance. The way we manage land and do agriculture is moving even more carbon from the soil and biosphere into the atmosphere. Specifically, we've moved 880 gigatons of carbon dioxide into the atmosphere, which is heating up the planet and destabilizing our climate. Now the oceans have absorbed a lot of this excess carbon, which is resulting in ocean acidification and accelerating a mass extinction of sea life. So in order to save life as we know it, of course, we have to stop releasing fossil carbon. The big question is, where do we put this excess carbon to get this cycle back into balance? Well, remember when I said that the solution is right under our feet? It literally is. It's the soil. Plants, with sunlight and water, perform photosynthesis. They pull in carbon from the air and turn it into carbohydrates, sugars. Then they pump some of those sugars down through their roots to feed microorganisms who use that carbon to build soil. Voila, carbon moved. Plants pump it in and soil stores it. Nature's living technology is amazing. Scientists have recently discovered that applying a thin layer of compost sets up an ongoing positive feedback loop that brings more and more carbon into the soil each year. In concert with other regenerative practices like not tilling the soil, planting trees, cover crops, and planned grazing, we can build and retain gigatons of soil carbon. This is carbon farming. This is regenerative agriculture. And there is nothing more powerful than an idea whose time has come. Unlike more carbon in the atmosphere, more carbon in the ground is good for us. It makes healthy soil, which is nutrient rich, full of life, and holds way more water. This means more nutritious food and crops that are more resilient in the face of drought. That's good news for farmers, families, and everyone that eats. Remember this, the way we grow our food, fiber, and fuel either puts carbon up into the atmosphere or it pulls it down into the ground. The regeneration of soil is the task of our generation. Our health, the health of our soils, and the health of our planet are one and the same.
So that's probably one of the most epic videos I've ever seen. Okay, so we looked at one of the primary ways the soil food web gets fed. It gets fed through the carbon cycle. So one adage in regenerative agriculture is roots in the ground year round. What that means is we want to maximize carbon potential in the soil, and we understand that a very easy way to do that is to maximize plants in that soil, because each of those plants is a carbon pump, pumping carbon from the air, and a portion of that carbon is exuded into the rhizosphere as sugars and carbohydrates, right? Okay, that feeds the soil food web, but doesn't really feed the plants. What that process is doing is it's building up the soil structure to be a better reservoir for nutrients and water, right? Plants need carbon, but they don't get carbon from the soil. They actually get it from the air. So the plants are getting all the carbon they need from just their cellular respiration, right? Breathing in carbon dioxide. The carbon they're exuding does feed the soil food web. Those sugars feed the bacteria, right? The bacteria are like the lowest trophic order in the soil food web. They eat the carbs and sugar exudates, and then their population grows, and then the next trophic order eats the bacteria, and then things that eat the bacteria are eaten by other things, right? So we build on that soil food web. But the byproduct of that is good soil structure, right, from the soil food web. The byproduct of that is increased organic matter. Carbon is organic matter, right, if it's exuded as an exudate. And then when it goes into the bodies of the organisms in the soil food web, those eventually die and decompose. So we're trapping carbon in the soil, and what that's doing is it's building the soil's holding capacity to hold more water, to hold more minerals, right? It eventually becomes what's called humus, and I think we read about that. Humus is fully decomposed organic matter. It's basically pure carbon. Okay, humus is has an incredible ability to attract nutrients and hold on to them through negative and positive charges. That's more on the chemistry side, and it has an incredible ability to absorb, hold, and store water. So carbon feeding the soil food web is going to improve the soil structure, but we also need to replenish minerals in our soil, right? Because we have what's in ecology, it's called the law of return. Okay, if we take something out of the system for long enough, we're going to deplete what it is we're taking out. So whether that's nitrogen, phosphorus, sulfur, etc. When we harvest crops and we take those to market, that represents nutrients being taken from our soil, right, and exported off site. You know, it's not coming back. So we need to replenish the soil with other minerals. Okay, and here's 3 of the main ones. So the one on the left is compost. Compost is basically organic matter, you know, fruit and veggie scraps and the like, that's gone through a decomposition process, and that process may or may not have been accelerated by an organism like a composting worm, right? We have vermicomposting where the worms accelerate that process, but the byproduct of that decomposition process is compost, and that compost has moderately high levels of nutrients in it. I think it's usually for like NPK, it's usually around 1 to 3%. So not as strong as like an organic fertilizer, but pretty high levels. So this stuff can be added moderately year after year to replenish nutrients in the soil. And remember, those nutrients aren't necessarily plant available. Those nutrients first go through the soil food web. They feed the soil food web, and then the soil food web biosynthesizes those organic minerals into plant available forms. We have animal litter. I think in that example it's poultry litter. So this is like a mixture of animal bedding, animal manures, animal urine that's been aged and decomposed over time. You do have to be pretty careful with this stuff. You want to know where it's coming from. So just for example, you know, like if you're getting horse manure, you really need to understand what those horses ate, right? If those horses are eating hay from a hay field that was sprayed with a broadleaf herbicide, that broadleaf herbicide, a typical one, Grazon, that broadleaf herbicide is very persistent. It's going to be in the hay, it's going to pass through the intestinal tract of the horse, and it's going to be in the manure for up to 5 years. Broadleaf herbicides kill broadleaf plants. Well, all the vegetables you're going to be growing in your garden most likely are broadleaf, unless you're growing like wheat or corn, which are grasses. So you want to know, you know, what did the animal eat? The hay that it used for bedding, was that from a pasture that was sprayed with Grazon, right? So we want to look at things that represent, you know, toxicity threats in animal manures. Other things to look at, you know, not all animal manures are the same. You know, they might have had a diet that was high in antibiotics. They might have been on a lot of medication. So it's best to know where you're sourcing that animal manure from, where'd the bedding come from, what'd the animals eat, what kind of environment is that originating from. Otherwise, animal manure is magical. It's how farmers maintain fertility for thousands of years. So it's an incredible source of fertility, but it's just unfortunate that with our more industrial approach to animal husbandry, more conventional approaches often lead to issues with toxicity. Bottom right, we have organic fertilizers. So organic soil amendments. These kind of fall into 2 buckets. We have geological amendments and biological amendments. So it either came from some sort of living, you know, organism, like feather meal comes from, you know, poultry feathers, blood meal comes from livestock blood, bone meal comes from crushed up animal bones, etc. For vegans, you might use more plant-based sources, like kelp, for example, comes from seaweed. So things that were once alive, those are biological amendments. And then we have geological amendments, things that come from geological deposits like salt deposits. So there's like organic potassium salts, there's organic rock phosphorus, organic trace minerals that come from a deposit called azomite. Okay, so different organic soil amendments used usually to bring up really deficient levels in the soil. Typically we can cover most of our fertility needs using some of these other strategies that are less expensive, but soil amendments can be used if you're really deficient in any one mineral. Okay, on the left here, what we're looking at is cover cropping. So cover cropping is a practice where we're growing a crop, but it's not an economical crop. It's not a crop we're going to sell. It's a crop that's going to give us what we call a lot of biomass, okay? Just a lot of plant matter. So these cover crops can be grown during the off season, like over the winter. People typically grow wheat, clover, vetch, rye, winter peas, and you can also grow cover crops in the summer too. But either way, when you grow a cover crop, you're kind of abiding by that rule of that best practice of keeping roots in the ground year round. You're trying to keep the space filled with some sort of plant, and cover crops typically do one of two things. They either fix nitrogen, right? Some plants have the ability to fix atmospheric nitrogen into the soil, or they're a biomass crop. They're a plant that grows a lot of biomass, and the more biomass, the more carbon, right? Carbon in the above ground parts, but also carbon in the root system, carbon being sequestered. So growing cover crops is a way to capture more carbon, and those cover crops are eventually terminated, like killed in other words, and reincorporated into the soil. In the top right, we have mulch. We talked about how mulch eventually decomposes and feeds the soil food web. So that definitely represents organic matter going back to the soil, going back to the soil food web. In the top right, we already talked about mulches, but yes, mulches are organic matter. Mulches will eventually decompose and go into the soil food web. In the bottom right, we have sheet mulching. This is a practice, it's a little labor intensive, but it can have its merits, especially if you really don't have any soil to begin with. It's a way of kind of building soil from the top down. So that bottom layer, imagine that's like an existing, spot in your yard, like some sod, some grass. What you can do is you can lay like a weed barrier down, like cardboard or newspaper, and start to smother out that grass, and then you can layer different types of materials, all organic matter, right? So you might have some alfalfa straw, you might have some wheat straw, you might have some animal manure, you might have some vermiculture compost, you might have a little bit of good topsoil, and then you're layering those different materials on top of each other, and all of that organic matter is quickly going to attract its own soil food web, and before you know it, that material will be almost homogenized. It'll all be broken down and decomposed and resemble basically great soil. There are some caveats with it, and we'll talk more about those in a later class. Okay, so now we're getting into the third bucket. We talked about the first, which was physical structure, soil structure, and how, what not to do to promote good soil structure, and how we need to employ the soil food web, which is the main driver, the main architect of good soil structure. We talked about the second bucket, which is soil biology, and how we have to feed that soil biology. We can't just not poison it, we also have to give it food. And by feeding it all of that good organic matter, that soil biology will in turn cycle those nutrients and make them plant available. And that leads us into chemistry. So chemistry is looking at the mineralogical components of the soil. Okay, so the main minerals in soil chemistry that we know are essential for plants to grow are our soil cations, our calcium, magnesium, potassium, and sodium, our anions, sulfur and phosphorus, our trace elements, which are boron, iron, manganese, copper, and zinc, and then also nitrogen. So we know that those are essential for plant growth. They all need to be there. We can reference Liebig's law of the minimum, which states it doesn't matter what your levels are of all the nutrients. If one is deficient, you'll be limited by that one deficiency. It doesn't matter if you have enough phosphorus, enough sulfur, enough calcium. If you don't have enough nitrogen, your plants are going to be limited in their growth. So your soils might have chemistry imbalances that need extra attention. So by and large, what I've always learned is that if you focus on building soil structure and you focus on the biology as the means to do that, the biology has a way of buffering minor imbalances in soil chemistry, right? It can kind of self-adjust. But if your soil's super out of whack, and that could be for a number of reasons, a chemistry test can tell you that. And if that's the case, you might require extra inputs of organic amendments, different fertilizers and pH adjusters to bring your soil back into balance from a chemistry standpoint. So getting a good soil test done can be paramount, for getting started, just to see where you're at. We definitely recommend using a lab that uses the Albrecht method of testing. So a lot of labs do that. Unfortunately, OSU Extension Office doesn't, so we have to send our tests off to, we use a lab in Ohio called Logan Labs, and tests are about $25. You can get a strong acid test or a weak acid test. If you're seriously considering getting a soil test, please let me know, and I can kind of help walk you through the specifics of what you're looking for. Soil is so much more than NPK, absolutely. So when you get a test, say at the Extension Office, what you're getting is an NPK panel, nitrogen, phosphate, and potash. You're getting a pH reading, and that's about it. So we're looking for a lot more than that. We want to know what's going on with calcium, magnesium, and sodium. We want to know what's going on with sulfur, and we want to know what's going on with our micronutrients, okay? So we want a full panel test. It's going to tell us a lot more. Yes, don't guess, test. So there's really, there's little way to discern where your soil is at from a chemistry standpoint just by looking at it. They say that you can taste your soil, and if it tastes sweet, it's alkaline, or if it tastes sour, it's acid, but just get a test done. Yes, tests that use the Albrecht methodology. So another big part of the Albrecht methodology is William Albrecht was a professor at the University of Missouri, Columbia, and he really pioneered soil science, right? Soil science is a fairly new emerging science, but he, in the early 20th century, was pioneering some really cool stuff with soil science. And basically what he did is he took all these different minerals and he put them in different proportions. He made these different types of soil mixes, and found like a curve where he saw optimum growth when the minerals were in certain proportions. And the big takeaway from that was that came down to a balance of the soil cations. So like on this soil test, you can see calcium, magnesium, potassium, and sodium. And then right below that, you see what's called base saturation. And basically that's speaking to the proportions that those salts, those cations, are in. So he determined that you want to have calcium and this is by molar weight. So that's a little bit complex to go over now, but essentially you want calcium saturation at 60 to 70%, magnesium at 10 to 20, potassium at 2 to 5, and sodium less than 3. So having those cations in those proportions is more conducive to plant health and higher yields and better plant growth. That's the idea behind it. So when we get these soil tests back, we can look at our base saturation and we can add certain cations, calcium, magnesium, potassium, sodium. We can adjust those by adding different amendments to our soils to try to bring those percentages within the targets. So again, if you want to get a soil test done and you need help going through that, I can definitely help you out. I can help you interpret your soil test and make recommendations on what you might need to add to bring your soil into better balance. Yes, we do help folks with soil testing services. So I'm very passionate about soil science, and I get really excited about the biology stuff, but I think the chemistry stuff is still pretty practical, So if you're interested in getting a soil test done, please let me know, and as part of the class, I'd be happy to look over your lab results. This is an excerpt from The Ideal Soil, which was written by Michael Estera, and it's all based off the William Albrecht methodology. If you want to get into understanding soil chemistry, this is a great place to start. Okay, so this is another cool excerpt. Hang on to this one. This is from The Ideal Soil. It's a list of all the amendments that are approved for use in organic agriculture. So you have the animal source amendments, the geological amendments, and micronutrient sulfates. So this is a pretty useful chart when you get your soil test back and you realize you need X amount of pounds of phosphorus. You can come to this chart and say, okay, well, so let's look at my phosphorus sources. Let's say I'm going for I want my food to be certified vegan, so I'm going to go down to a phosphorus source from a geological source. So I'm going to go with the CalPhos, right, which is a rock phosphorus. So eventually it'll have 20% available. So let's say I needed 20 pounds of phosphorus for my plot. I've calculated that for the amount of square footage I have in my plot, I need 20 pounds of pure phosphorus, and it's more accurately phosphate. So I go over to CalPhos and I see that it's only 20% phosphate, but I need 20 pounds of phosphate. So how many pounds of CalPhos do I need? So I divide 20 by 0.2, and I'm going to realize that I need actually 100 pounds of CalPhos to supply 20 pounds of phosphate to my garden space. So that's kind of how that works. But again, if you want to get a soil test done, I can help you understand the numbers and how to move forward with those. Korean natural farming, wow, this stuff is really cool. We're actually going to cover this in the fertility and pest management class. We're going to look at all these different homemade fertilizers that they use, but in the meanwhile, just Google this stuff. It's really, really neat. The University of Hawaii has some really good publications on Korean natural farming, but this is basically how one of the ways folks in Asia has a very long history of agriculture and sustainable agriculture. Actually, the organic agriculture movement was really born out of observations from traditional Chinese farming practices. So before they industrialized agriculture, this is a big way that farms in Asia met their fertility needs. It uses mostly local and free materials. It is mostly coming from the tropics, so or more tropical climates, subtropical climates. That's where it's the most popular. So it does need a little bit of adaptation for temperate climates to make use of the biological materials that we have. But basically you use all these materials and you make all these preparations and ferments, and you dilute them with water and apply them as foliar sprays to your plants and soil drenches. So very, very interesting, worth looking at more, and we definitely will in the coming weeks. Solarization. So I guess this is kind of getting into how do we do no-till, right? Like, don't we till to like disturb the ground and get rid of the weeds? Yes, we do. And in no-till, we can't use a tiller, so we have to come up with other disturbance techniques. We'll be covering this on the bed preparation class. Yep, this is another part of that, and we'll be covering that on the bed preparation class. So I guess just rest assured that there are indeed ways to still farm without using a tiller. In a lot of ways, they're easier, and they're definitely a lot more quiet. Hey, this is a cool tool. This is a broad fork. So this is another technology that we use to promote soil health. What it does is, if you do have one of those hard pan layers, as a result of tillage, this is a deep fork that goes down into the ground, and then you leverage your weight on it, and it kind of lifts, kind of breaks through that hard pan and kind of uplifts the soil, allowing air to get into the soil. It's kind of like a chiropractic readjustment for the soil. It's a lot of work, but it's a very useful tool. These are some other tools that are going to come into use with no-till farming. We'll learn about each and every one of those. Folks, so that concludes the presentation for soil. Hopefully you're walking away with a better grasp. I do suggest that you re-watch the presentation. That should fit into your 4-hour class window. Watching it again is just going to kind of help hammer in those concepts. There's a lot of pieces, and it takes kind of a holistic viewpoint to make the connections. So it's even helpful for me to watch these videos over and over again. So with that said, thank you so much for your flexibility. I really do value the experiential learning component associated with this course, the hands-on component. It's really hard to trump that. Just given the circumstances, we're going to have to hang tight and be as resilient as possible. I think you were able to pick up a lot today from the presentation. I can promise you that eventually, when we do get back together, we will revisit these concepts through a more hands-on approach. But in the meanwhile, I want to give you a few things you can do to kind of further your grasp until we can meet again. So I did include a write-in assignment in the email, so go ahead and check that out. Try to get that done this week. The second thing I want you to do is hands-on. Everybody can go outside and probe around your yard, your garden if you have one. I want you to look at different areas of your yard, and I want you to look at the soil. I want you to see if you can find any of the, if you can identify any of the criteria that we covered today. Can you identify aggregation? Can you see any soil organisms or proof of soil organisms? Can you see differences in organic matter? Can you see differences in texture? Can you make assumptions about the infiltration of a certain soil? Take an area in your yard versus an area in your flower beds. Contrast that with maybe an area where that gets a lot of foot traffic. So just get outside, be playful, explore the soil. You might learn something new that we didn't even cover just from that observation exercise. So without saying too much more, I will be sending you your second reading assignment for the next course, the next class rather. and we will schedule that for 2 weeks from today. And I'm hoping that we can design the class in such a way that allows us to meet in person, but we're just gonna have to hang tight and see. So bear with me, and look out for the reading. It'll be coming soon. Thank you all so much for being here today.